Okay, today we finished our discussion of lift forces, and just to be clear here, lift forces are created when an object is approached by fluid flow. The lift force is specifically the component of the force that's perpendicular to the direction of the flow. Remember, our drag force was the component in the direction of flow. What we need for a lift force, in this case to be upwards, we need the pressure to be elevated on the underside and reduced on the upper side, and that's going to create that net upwards force. Talked about two different ways of creating that, but both of them involve the specification of a lift coefficient. So we say the lift force is equal to a lift coefficient times some area times 1/2 rho u0 squared, very much like the drag force formulation that we did previously. So two different cases that we talked about in class. One is a rotating object, or a cylinder, or a sphere. So this would be the case of the sports balls, or just a rotating cylinder in general. For that case, we have a circular object that's rotating with some circulation rate gamma, and the lift force works out to be the density of the fluid times the velocity of the fluid times that rotation rate times the length into and out of the board. This is for a cylinder of length L. That means that the lift coefficient is a function of the rotation rate, the radius of the cylinder, the rotation rate, and the approach velocity. The usual way this is done, and I'll just note this briefly, is lift coefficient is a function of this dimensionless group, angular velocity over approach velocity, has some kind of functional form like so. We talked a lot about the physics of how that lift is created. In the end, this empirical result works pretty well. The other example is for the case of airfoils or wings, where we have an airfoil, sketched rather poorly here, of chord length C and length L into and out of the screen, and then an angle alpha defining the angle of attack that this makes with the horizontal. In this case, the lift force works out to be density times velocity squared, pi times the chord length times the length into and out of the screen times alpha, or the lift coefficient, quite simply, is just 2 pi times the angle of attack. Now, there's a bunch of other factors that come in here when alpha gets to be too large. Drag forces start to play a role. Separation can really get changed if alpha gets too large, and that's when stall sets in. But at small angles, this works well. For rotating cylinders or spheres, we have this formulation. And in the end, in all of these cases, we just use our lift force formulation that's directly analogous to the drag force formulation.